Okay, it's time to begin. Just to make sure that I am on the same page as everyone else, I have, first of all, people I don't see here are Chad, Helena, Sally, and Cassie. Is that okay? 2 notes here. One, the lab posters are due today. Those lab posters should be posters that show what you did, talk about the theory of how it worked, explain the physics, that's the important part. And they need to be turned in. I have to give them to Dr. McNeil by 3. So that's why I put the 2:30 deadline. So make sure you get them to me. You should be able to turn them in on the class on Moodle. Had my hand slapped, but I don't think they've changed it back when I raised it to make this file size big enough for you to submit them. You only need to have one person in your group submit, because it'd just be the same thing multiple times, and the key here is to turn it in. If you can't get it turned in on Moodle for whatever reason, you can share it with me, share it to riweb@ucause.edu using Google Drive, or you can bring a thumb drive by my office. But we need to get them because Dr. McNeil is going to leave, I think, at 3 to drive over to UNL and deliver them to them. Second thing, we will review again on Monday, and for Wednesday, make sure that you have done Concept Coach through Chapter 32, Section 4. So I'm making sure I'm ahead of the game here a little bit. Any questions about those 2 things? All right, I thought they'd be clear, but it's best to check. Okay, we're talking nuclear physics here, and so one of the first things that I need to talk about today is how we define or describe a nucleus. So the nucleus, everybody knows. Everybody in this class, I'm pretty confident, knows. The nucleus of an atom contains protons and neutrons. And it's shaped roughly like a sphere. And it's been determined experimentally that the radius of that sphere is roughly equal to, our textbook puts the equal sign, so I copied the textbook and my sign, roughly equal to 12 FM times a raised to the 1/3. Go through this. What does FM mean? Not Faro. Okay, femtometers or a Fermi, named after Enrico Fermi. You can use either name. In each case, it means 10 to the minus 15 meters. I've defined here on this page. We have 3 numbers that we use to define the nucleus. One of them is redundant. We have the atomic number. The atomic number is the number of protons in a nucleus. The atomic number tells us the element. If you look at the periodic table of elements back there, the elements are numbered 1, 2, 3, 4, 5, 6, 7. That's telling you how many protons are in the nucleus. Now, I told you before that the periodic table was actually made up based on the electron energy states. Well, its original development was simply based on the chemical properties. They looked at property. This one here is the Mendelevian periodic table. There are other ones. My favorite one is the one Lothar made, but not Lothar of the Hill people. And his had a big spiral because it really does wrap around. But what Mendeleev did was he tried to put elements that had roughly the same properties in the same column, that's chemical properties, and then he arranged them downward by mass, so the lower you went, the more massive it became, and going to the right by mass. So he came up with something similar to this. This is not Mendeleev's table, but it's, it's the descendant of it. And so we have over here, the things that are alkali metals, and what's the next one? Alkaline or something like that?
Alkali earth metals.
alkali earth metals. And then you have your, transition metals. And I don't remember all the names of all these columns. It's been years since I've taken chemistry until we get to the noble gases. So each element, vanadium, has 23 protons. Doesn't matter how many neutrons it has in it, it's vanadium if it has 23 protons. It can have different numbers of neutrons. So we talk about elements that have different numbers of neutrons but the same number of protons as different isotopes of the same element. So isotope, well, you know iso means same. And isotopes have the same atomic number. So I have different isotopes of, for instance, hydrogen. Who knows what the three isotopes of hydrogen are? We have different names for them. Yeah, there's hydronium, deuterium, and tritium. There are three isotopes. What's the difference? Well, it's pretty clear. Deut, 2. It has two things in the nucleus. But if it's an isotope of hydrogen, only one of those things is a proton. So the other thing's a neutron. So deuterium has one proton, one neutron. Tritium, tri-3, has three things in the nucleus. Since it's an isotope of hydrogen, one is a proton, so the other two have to be neutrons. Okay, then you also have something that's called isotones, which is the same number of neutrons. But that's not nearly as fun to deal with. Nobody talks about isotones. I doubt it's in our textbook. You change the P for proton to an N for neutron. Tricky that way, huh? So Z, the atomic number, is really important because it tells us about the chemical properties. Why does the number of protons in the nucleus tell about the chemical properties? What do the chemical properties have to do with? The electrons. But for a neutral element, the number of electrons is going to be the same as the number of protons. So knowing the number of protons tells us how many electrons it has if it's neutral, and thus tells us what its chemistry is going to be. Okay, the neutron number, how many neutrons it has, and then A, the atomic number, or atomic mass number, atomic number is number of protons, atomic mass number. Sometimes people will take off the atomic just so we don't have it in two of the names, make them sound so similar. The atomic mass number tells us the total number of nucleons. So there's a simple math, A is equal to Z plus N. So if you know two of those, you obviously know the third because of that simple equation. And the way we identify a nucleus, I don't like that color. The way we identify a nucleus is by writing it with superscripts and subscripts. Our textbook actually does the subscript N. Every other textbook I've ever seen uses superscript N. But you know what? People never write the N. In fact, you really only need one number to uniquely identify the nucleus if you tell us what the element is. If I say carbon 14, what does the name carbon imply? The number of protons. Carbon, I look back there, carbon always has 6 protons because the atomic number tells us the element. So if it's carbon, I know it had 6 protons. Carbon 12 means it has 12 nucleons. So the number of neutrons must be 12 minus 6 is 6. Carbon 14 has 14 nucleons. Number of neutrons must be 14 minus 6 is 8. So the symbol tells us the number of nucleons. So these two are perfectly redundant. If you know Z, you know X. X being a placeholder for the symbol. If you know the symbol, you know Z. And then all you need is one other number, and it's completely described. So most often, people will simply say the total atomic mass, or mass number, and the element, and that's enough. But it's important to know what these nomenclatures are, and hence our first clicker question. Oh, it does not come next, but it's coming soon because it's on that topic. Unless somehow I screwed up and I don't have it here, but I don't think I did. We'll see. So, decays. When a nucleus decays, it will only occur spontaneously if you're going to a lower energy. And Einstein is the one that gave us a key to figure out how that energy relates. Einstein said that mass is just a form of energy. And so we talk about the disintegration energy. Most textbooks I've used use Q for this, or disintegration energy. That's, yeah, close enough. But that energy released is the mass of the parent minus the mass of the daughter times c squared. So let's take as an example, let's say that I have uranium-238 decays to give me thorium-234 plus an alpha particle. Now, one of the first things I have to do is I do have to count for electrons, because the difference in mass is not going to be huge. So how many electrons does uranium-238 have? Yes, good move. Turning around, it's 92, and I'm going to write in red 92 protons for the uranium. The thorium has 90. The alpha has 2. Alpha is a 2,4. We have certain conservation rules we have to have. Conservation rules, conservation of baryons. Baryons are the heavy particles. Until we get to, what is it, chapter 33 or 34, for you, baryons will just be protons and neutrons. And so you have to have the same baryon number before and after. So how many baryons did we start with? What is a baryon? Protons or neutrons. And so what number tells us the number of protons and neutrons? This one. So we started with 238 baryons. How many did we end up with? 234 plus 4, 238. Okay? That worked out. Now we also have to have conservation of charge. And so if we start here with 92 protons, how many electrons did we probably have with it? 92. So we had, neutral, 92 electrons there. We have 90 protons here. How many electrons should the thorium have? It's still going to have, got to change back to the pin, it's going to have a -2 charge initially because it's going to have the extra 2 electrons at the instant that it's made. What about the alpha particle? It's a +2 because it has no electrons. So now the number of protons was the same on both sides, so we don't have to worry about counting those. For the electrons, we have thorium with an extra 2 electrons and alpha missing 2 electrons. Well, in terms of math, that's the same as having thorium with its correct amount of electrons and the alpha with its correct amount of electrons. So in terms of math, as long as I make sure I balance my electrons, I can find the most convenient way. So to do this, I'm going to say the energy released is equal to the mass of plutonium, no, it was uranium, uranium-238 minus the mass of thorium-234 plus helium-4. Right, I put helium-4 because that's what I'd have if I took the alpha particle and put 2 electrons on it. So I took the 2 electrons off the thorium and put them on the alpha for my math. And then I need to multiply that by speed of light squared. Well, I need those numbers. I do have on the next slide where you get the numbers. I have the 2 web pages on the next slide already open. So I'm going to shift over real quick to... Come on, come back to me. Two different tables. The one on the left is the table from your textbook. Really? Well, when that happens, you turn it off, and you turn it back on, and what can go wrong? I mean, lots of things, but it's not going to. Yay! Okay, so here are two different tables. The one on the left is the table from the back of our book. The table from the back of our book is really nice in that it tells us things like the radioactive decays. If you look, for instance, at tritium. Tritium, you put H with superscript 3 in front, or there's a symbol T since it's used. We have some tritium over there. It decays with A, and it tells you a beta. From this distance, it looked like a minus. Yeah, decays with a beta minus decay. And it tells you the half-life. That tritium will stick around for about 12.33 years. Before, if it's a half-life, how much is gone after 12.33 years? Half of it, right. How old do you suppose that beaker is filled with tritium in there? It's probably about 60 years old. 60 years old, it's gone through approximately 5 half-lives. Going through 5 half-lives, 1/2 raised to the 5th, there's not much of the original activity, but it's still present. Okay, let's get to what we're doing for this problem. We're looking at helium-4. So the mass over here, it says 4.002603 atomic mass units. If we look on the other side for helium-4, it gives me some more decimal places. Why? Because the one on the right is the National Institute of Standards. That's the best knowledge we have for what its value is. So the safest thing for me to do is going to be use all of those digits. And so I'm going to say, and I'm writing this down so you'll see it later, 4.002603.25413 atomic mass units. That's the mass of the helium-4. I need the mass of my thorium-234 and the mass of uranium-238. So I scroll down, and once again, both of these are going to have them. So here's uranium. Uranium-238 is 238.0507884 atomic mass units. And the thorium-234 is 234.0436014. If I would have come on this one, it doesn't have nearly as many elements shown, but you see the uranium-238, and it shows us that it has an alpha decay with a half-life of roughly 4.5 billion years. If you have uranium-238, how long do you have to wait for the activity to drop off to nothing? Yeah, forever, basically. Many times the age of the universe as scientists believe it to be. If you wait, uranium that was created on the day the universe was born would still be less than 3 half-lives old. Okay, and thorium, likewise, here's the thorium, and this doesn't even show thorium-234. Doesn't show everything. That's why I went to the National Institute of Standards. Okay, change back. Now, how do we do the math here? This thing is called the mass defect. I need to calculate that mass defect because it's the difference in the mass from the beginning side to the ending side. So I'm just going to calculate the mass defect. Delta M, as our textbook calls it, is going to be this one on the bottom minus the 2 above. And so I just have to go through and do that math. Now, of course, how am I going to do that math? I'm actually going to pull up a spreadsheet on the computer. You won't see the spreadsheet. Why do I do it on the computer? Because I am bound to make a mistake. I know I could have asked somebody else to do it, but And that gives me a mass defect of, hey Sally, 0.0045837,459 atomic mass units. How many significant digits do I have in that answer? This here is 7. It should be 7.
Okay, I wasn't sure if that was a 4 or a U because the others had U's after them.
Yeah, I forgot to put the U there. So I should have it out to the 7th decimal place. So 1, 2, 3, 4, 5, 6, 7. It's good out to here. And so to correct significant digits, that's now only 5 significant digits in my answer. Notice I had to use a lot of significant digits in my masses to get 5 significant digits in my answer. I could have cut off a couple and had 3 if I wanted, but 4 is like the minimum I want to keep when I'm doing a problem. And this is as good as we know right here. So if that's delta M, then the energy released, that's not how you spell released. Now I'm going to copy this onto the next slide because the next slide has the numbers we're going to use. So let's go to the next slide. And, oh wait, now we have my clicker question. Then the next slide will continue on. I knew I shouldn't have separated things. Okay, so we will do the clicker question so I don't forget it. A hypothetical element is identified as X9756. How many protons does this element contain? Okay, so there's our answers. Let's go through how we find the answer here. Actually, no, discuss it. Discuss it among yourselves. Discuss how you came up with your answer and what the correct one is. All right, let's give her a second shot. And let's do better. Cassie. Okay. After repolling, we had very little change, except for one more person answered. Okay. I think there weren't many people following when I was describing this. We have three numbers, A, Z, and N. What does A stand for? Okay, it's the atomic mass number. How do you find the atomic mass number?
Neutrons and protons added together.
It's what?
The number of neutrons and the number of protons.
Okay, it is the number of neutrons and protons added together, so we have A is equal to Z plus N. When we read that symbol, how do we read it off of the symbol?
A is the upper left-hand corner.
Okay, upper left-hand corner. So we can read directly that A is 97. What is Z?
A minus N.
Well, yes. What does Z stand for? It's the protons. It's the atomic number. It's telling us how many protons are in it. And so that's what we were asked for. How do we know the number of protons by reading it?
Bottom left.
Bottom left. That was blank. What else tells us?
The atomic mass is minus N.
Well, from reading, it's the symbol. Remember I said that these two things are absolutely redundant. But X is not a symbol for an element, that's a placeholder. So I didn't give you that. So let's go on to N. What is N? It's the number of neutrons. It's the neutron number. The third one was very good. That was so astute. So how do I find the neutron number from the way we write it?
Bottom right.
Okay, it's the bottom right. So the neutron number was 56. Well, since we've identified two of the three, we can find the missing one by doing, as Tori mentioned a while back, Z is equal to A minus N. And so we did have a slight improvement toward the correct answer. It was improvement. All right, now continuing our calculation that we so rudely interrupted. Masses. How do we identify the mass? Well, atomic mass unit, also known as Daltons, if you study that in chemistry or in biology, Daltons is just another name for atomic mass unit. The atomic mass units are defined using carbon-12. Specifically, you have the definition that 1 mole of carbon-12 has a mass of 12 grams. Exactly. And 1 atom of carbon-12 has a mass of 12 atomic mass units. Exactly. That's how we define the atomic mass unit. Well, what's the relationship between a mole and an atom? Avogadro's number. So we can make an equation that says the molar mass, the mass of 1 mole, is equal to Avogadro's number times the mass of a single atom. Therefore, 12 grams exactly is equal to Avogadro's number times 12 atomic mass units exactly. And then solving that for what an atomic mass unit is, divide both sides by 12 and by Avogadro's number, and you get 1 atomic mass unit is equal to 1 gram divided by Avogadro's number. So that's the definition of atomic mass unit. If you know Avogadro's number, you know the atomic mass unit. And so I worked it out here, 1 atomic mass unit, 1 gram over Avogadro's number. Put in Avogadro's number to a whole bunch of digits so I could get the mass, 1 atomic mass unit to a whole bunch of digits. Notice I put it in grams. Up above, numbers are in kilograms. As long as you know what you're working with, it's good. But you know what? Since we're using Einstein's E equals mc squared, it's really convenient to, instead of using kilograms or grams, to use units of mega electron volts divided by c squared. So that's what we generally do. We simply take the atomic mass units, convert them to MeV per c squared, multiply by c squared, and the c squareds cancel, and we have the energy. So that's what we're going to do here. So paste my equation from the preceding page. That's going to be equal to, come on, (931.4941). Now let's just look at the units here. I have atomic mass units here, per atomic mass unit there. So those cancel. I had over c squared here and times c squared there. Those cancel. And what I'm left with is going to be an answer in mega electron volts. So if I go back to my spreadsheet and I take that mass and I multiply it by bet you've never seen anyone who does everything on a spreadsheet like me. Okay, how many significant digits do I still have in my answer? Just 5. So let me take off the extra digit that was insignificant, and that's the energy released when the uranium-238 decays into the thorium-234. That's how we calculate the energy released when we have a radioactive decay. And radioactive decay will only occur if the energy goes down. If the energy goes up, well, it's not going to decay. You could have something make it happen if you put energy in, but it's not just going to decay on its own. So that's what was going on with the samples we used in lab on Tuesday. I had these samples, and I bombarded them with neutrons, and some of those would get absorbed, making it a different isotope, and that isotope was unstable, and then it would decay. But that absorbing the neutron, that was not energetically favorable, but because I was hitting them hard, I put the energy in. You may have seen this before, especially if you've turned around and looked at the back of the classroom. The back of the classroom, there is a chart that has this information, although it doesn't have the same scale, so you don't see that it is steep. If you compare the number of protons to the number of neutrons in stable nuclei, for low masses, they're basically the same. So for instance, helium, 2 and 2. And carbon, 6 and 6. Nitrogen, 7 and 7, for the most stable isotopes. But as you get bigger, that pattern breaks. And you start having more and more and more neutrons. Who has noticed this before? Who has understood why? Well, the answers that we have come from the work of people like Maria Gabbert Meyer, who's going to be on the next slide, Enrico Fermi coming up after that. We know right now about two forces, two fundamental forces. What are the two fundamental forces? We've studied a lot. Okay, the electrostatic force and gravity. Okay, so with the nucleus, we're going to have these forces because they're forces that happen between things with a mass or a charge. The nucleons have mass and they have charge. Which one's going to be stronger, the electrostatic force or the gravitational force? The electrostatic is far stronger, and so we're going to completely ignore the gravitational. You have electrostatic force. But we're in a nucleus. What kind of things do you have in the nucleus? Only two types. What are they? Okay, we have positive protons and neutral neutrons. Well, left by themselves, what are the protons going to do to each other? Push it apart. So we have to have something to glue them together because the electrostatic force is going to push them apart. Well, what's holding them together? Scientists have identified two forces that hold the nucleus together. We only have 4 fundamental forces that we know of, and those 4 forces are the two we talked about and the weak nuclear force and the strong nuclear force. Oftentimes people just call these the weak force and the strong force. These are the forces that hold the nucleons together. And these forces have a different type of charge. What was the charge associated with gravitational force? Mass. The charge associated with electromagnetic force? Yeah. What we usually just call charge. Well, the charge associated with these forces are the little things that make up the protons and the neutrons. And so we're going to have attraction between protons exactly the same as we have attraction between neutrons. So protons and neutrons are attracted by these forces. But there's a difference. These are very, very short-range forces. Effectively only affects your nearest neighbor. So we can think of this, we have a short-range attractive force. Let's look at this row here where we have three gentlemen. The gentlemen are, let's say, a positive, or excuse me, we're going to make a positive charge for Ray, positive influence, and a neutral charge for Zach and for Austin. What kind of interaction would they have from electrostatic force? He's positive and you're neutral. What kind of force do you have? Nothing. So electrostatically, there's no force. Nothing pushing them apart. But because you have a nearest neighbor force, there's a force that's going to pull Austin to Reagan, pulling them together, the strong weak nuclear forces. And a force that's going to pull Zach and Reagan together. So they'll hold together nice and easily. And thus we have a tritium. Now let's reverse this. Let's now make Reagan neutral and Zach and Austin positive. Is there a force between Reagan and Austin? Not electrostatic. But because they're neighbors, there's still an attractive force from the strong nuclear force and weak nuclear force. Likewise, between Zach and Reagan, there's an attractive force for the nuclear forces. So they're pulled together, but what about between Zach and Austin? They're being repelled. And so it comes down to what is going to win out. Well, the strong and weak nuclear forces are stronger. And so in this situation, because they're separated, the electrostatic force is smaller, and they're going to hold together, and we're going to have ourselves a nice neutral, or not neutral, a nice stable helium-3 nucleus. But if we started to do something crazy, like let's say we have an iron nucleus, and in iron we have 26 protons. Those protons are all trying to push the other protons away. If you had just 26 protons, the forces trying to repel them would be enormous, and it would fall apart regardless of all of the attractive forces from the strong nuclear force and weak nuclear force. Well, what do? We throw some neutrons in between. Throw the neutrons in between, you space out the repulsive forces. And thus you weaken them, and putting that neutron in between, you have holding everything together. And so the more neutrons you put in, the weaker the repulsive force is and the more stable it gets to a point. And so that's why we have, for big charges in the nucleus like iron or like uranium, there's a lot more neutrons than there are protons to get the positive charges farther away and lower the repulsive forces. So that's the explanation for why they don't just fall on this nice simple line like it seems they start out with. So a little history here. Maria Gabbert Meyer. Now, Maria Gabbert Meyer is a classic physics story of misogyny. Maria Gabbert Meyer came up with a shell model to explain how the nucleus works, for which she earned a Nobel Prize. But it wasn't until the very end of her life that she was ever paid a full professor's salary, because her husband was a professor, and they had rules, much like the Seventh-day Adventist Church did when I was a child, that if you had two members of the family working in the same place, only the first one, which was the man, could get full wages. The second one would have to get half wages. And so, here we have a Nobel Prize winner not getting full wages because of her husband also being employed. You guys obviously weren't alive here, but when I was a child, Mary Kay, I think that's like her last name, sued the Seventh-day Adventist Church because of that policy. And since then, the Seventh-day Adventist Church has moved to, if both spouses work at the school, they'll both get paid. Instead of, well, the idea the church had was a family only needs X amount of money, and so you don't need that extra money. But it was thrown out on being sexist, which I'm sure it was. Oh, yeah, I talked about her history, about what she did in physics, that shell model. Okay, another thing that's really funny about this. She started explaining the nucleus like we talk about the electrons. We talked about the electrons and we had shells and subshells and these quantum numbers. She said, looking at the organization of stable nuclei, I think that there are quantum numbers involved with the nucleus, and there are shells, and you get a complete shell, and it's more stable, just like with the electrons. Well, she did this during the Cold War era. And so during this time, everybody's building bombs, and nobody's trusting anyone. And so the Russians get this report of the shell model, and of course, we have the atomic bombs that have just been developed, and they're thinking, it's the bomb model. There's something about bombs in the nucleus. And it actually delayed them understanding the model by a few years because it was mistranslated because of the climate in the world at that time. But she is the person who has the Nobel Prize for helping us to understand that the nucleus has its own quantum physics going on with quantum numbers to explain the energy states. And then we have, well, uranium decay sequence. Because we're going to go to Enrico Fermi, who is the godfather of nuclear energy. So, uranium. Everybody knows. Uranium, you can make bombs from it, right? Well, uranium comes in two semi-common isotopes. There's uranium-238 and uranium-235. Uranium-238 has a very long half-life, 4.5 billion years. Uranium-235, much less, which means that most of your uranium is uranium-238. That uranium, both uranium-238 and uranium-235, go through similar decay sequences. It decays from uranium to thorium. That's the one we did the equation for, giving off a particle, an alpha particle, with an energy that was a little above 4 electron or mega electron volts. Then it gives off a beta particle twice. And you can see the half-life sitting there. 24 days to go from thorium to, what is PA? I don't even know what PA is. Yeah, I should know that. I think it's like the guy, I don't know. Then another 6.7 hours to get to uranium-234. Nobody talks about uranium-234. Why? Because its half-life is 250,000 years. And you're saying, 250,000 years, that's a long time. I'm not going to live that long. But compared to the half-life of uranium-238, 4.5 billion years, that's a blink of the eye. And so these times, especially the time that thorium exists, minuscule compared to the lifetime of the uranium. Hence, we never expect to see much thorium-234 because it's made rarely and then it disappears quickly. So we come down that sequence and you can see the lifetimes get shorter and shorter as you get down to the end and you end up with lead. So we often think of this decay as the decay from uranium to lead because that's the starting and ending points. And the half-life is just the half-life of the longest one. So the first one is the half-life we consider for this reaction. But we have sequences of decays like this, and that's the key to nuclear energy. So here's a picture of Enrico Fermi. He worked at the University of Chicago. He made the first nuclear pile. Put a whole bunch of nuclear material on there, and oh, it gets hot. He made it a racquetball court under the football field, I think it was, or something like that. When they started the Manhattan Project, they started it up there at University of Chicago. You guys know what the Manhattan Project is? Making a nuclear bomb, for anyone who didn't recognize that. When they started the process of making a nuclear bomb, they started there at his University of Chicago. And then they realized, wait a minute, we're doing some things that are pretty dangerous. Maybe we shouldn't do this in Chicago, which was the second largest city in the United States at that time. So they moved out to the middle of nowhere, a place we like to call New Mexico. And then they worked out there in isolation. So if something went wrong, and there were accidents. There's the famous accident of letting two things get too close and a lot of radiation, and he died digging them apart with his hands and getting so much doses that he died. But he saved everyone else. But they moved it out there to keep things safe. So he's the one who identified the weak nuclear force that we were talking about, did a lot of experimental work getting the world started on nuclear reactions. I've already looked at an alpha decay. Alpha decay, we had just the hydrogen, the helium nucleus coming out of the nucleus. I know I said that, it is still correct. You had a nucleus breaking into two, but one was really small. Beta decay is interesting. This particle here, initially people looked at beta decay, they see the nucleus, they see the new nucleus, and they see the electron, and they say, that's it. But then with careful observation, careful experimentation, they found the problem. Energy and momentum weren't conserved. And so the scientists were stuck with one of two options. Either what we believe are fundamental underpinnings of science were wrong, or there's another particle that we haven't found. Well, which one's the easy one to believe? The second one. And so they theorized that there must be this little tiny particle with really low mass, because if it had big mass, they'd find it. And it has to have a neutral charge, because if it had a positive or negative charge, they'd find it easily. So it had to be something that essentially doesn't interact with anything. And so they gave it a name of neutrino. Neut for neutral, ino for a diminutive suffix. And so the symbol for the neutrino is the Greek letter nu. That's what that is, not a V. And the bar over the top means anti. This is an anti-neutrino. The subscript E, by the way, means electron. It's an electron neutrino. Later on, they discovered that there are 3 flavors of leptons, the electron, the muon, and the tauon. And each flavor has its own neutrino. So there's the electron neutrino, the mu neutrino, and the tau neutrino. So that's why it's labeled that way. They have measured them. They measure them a lot now. But they're going through you right now. Right now, you have lots of neutrinos just flying right through your bodies. But the key is, they're neutral and tiny, they don't interact with us. So they just go through. It kind of feels weird to say that I am currently having lots of things go through my body. But that is our understanding. They're going right through. They do experiments. The experiment where they thought the neutrino might be going faster than the speed of light that I talked about earlier. They made the neutrinos, I think, at CERN, and they detected them somewhere on the other side of the globe. The neutrinos, they just aim that beam right through the Earth. They don't care. It's going to go right through the Earth. And then they aim it at the lab, and they measure at the lab. So that's what a beta decay looks like, a beta minus. What's an example of a beta minus? Well, carbon 14. How many protons does carbon 14 have? 6. It's unstable. And so it becomes nitrogen. How many protons does nitrogen have? 7 protons. Nitrogen 14. An electron is not a proton, right? But we put a -1 here for record keeping. That's the way we write the equation. so that we have 6 is equal to 7 plus a minus 1. What really happened there was a proton was created by annihilating a neutron and creating the proton and the electron antineutrino. So it's a pretty complicated process. It's not like the alpha particle where something that was in the nucleus came out of the nucleus. This is where something was created in the nucleus and then came out. Yeah?
I'm sorry, what did you say made the not antineutrinos, the normal neutrinos again?
What was that?
What did you say made the normal neutrinos again? Because I see that's the antineutrino.
Well, there's conservation of lepton number. And so you have to have a lepton with an anti-lepton so that the total lepton number is 0.
Okay.
We haven't gotten to that clearly. Oh, and I'm sad because I have another bunch of slides. Here's a beta plus decay. I am going to skip over the beta plus decay to end the lecture by talking about radiometric dating and having one last clicker question. Radiometric dating relies on the decay of radioactive elements, like you studied in lab on Tuesday. And so for radiometric dating, which was only invented in the 1950s, you have to know how much you started with and how much you ended with. There's a lot of difficulties in finding that we don't have time to go through. But a key here is that over time, each half-life you have half as much left. So you take each one and the amount remaining is equal to the amount you started with times 1/2 raised to the time divided by the half-life. And so our clicker question is going to deal with this equation here. Remember, just 1/2 raised to the power. And so the question is, and give me a second, more than a second. It's, goodness, there it is. Approximately how many half-lives result in less than 0.1% of the original nuclei remaining? And in case you answered before I got there, only Diksha's answered at this point.
Sorry.
No, there's nothing wrong with answering.
Well, I was like, I think you said it was wrong. I was like,
No,
oh.
no. It was because it took me a while to get there.
Sorry.
Okay, I'm going to only give you about 10 more seconds because class is, I'm over time. Okay, our answers were all over the road. The correct answer was 10 because 1/2 raised to the 10th power was 1024, something in that ballpark. And so that's going to take you to less than 1/1000th. I'm going to end on this slide with the Shroud of Turin. The Shroud of Turin was something that was discovered in the 14th century, sometime in the 1300s. It was not carbon dated until 1988, which is a delay of about 30 to 40 years from when carbon dating first came around. When they did the dating, they found that it was at its very oldest from about 1,260 years after the birth of Christ. That would not make it the shroud he was buried in. But there's still controversy. One of the primary controversies is they cut out a little sample of the shroud, and the fabric of that little sample doesn't match the fabric other places, so they think that the sample that they actually tested was not part of the original shroud, but maybe somebody tried to repair it when it was first discovered, and they did their testing on the repair job that was done when it was first discovered. So one would have to say that the actual radiometric dating for the Shroud of Turin is still not well known. It is also pretty inconceivable that we would have enough knowledge to say that this cloth that was found in the 14th century is the cloth that Christ was buried in. Right? It's kind of a stretch. But that is the story on it. So some people believe that if you look at this picture, you're looking at what Jesus' face looked like. Okay, we are out of time. I'm sorry I went over.
I have to go out 5 minutes earlier.